Hi everyone, welcome back. In this lecture, we will understand Docker architecture with this simple diagram. Let's understand Docker architecture step by step. First, we have the developer. The developer creates an application and uses Docker commands to package and run it. For example, the developer may execute a Docker build to create an image, Docker run to start a container, or Docker pull to download an image. These commands are sent to the Docker client. The Docker client is the command line interface that accepts Docker commands. When we install Docker and execute a command in the terminal, we are interacting with the Docker client. The client does not perform the container operations itself. It converts the command into an API request and sends it to the Docker daemon through the Docker API. Next, we have the Docker daemon. The Docker daemon is the background service that performs the actual work. It receives requests from the Docker client and manages Docker objects such as images, containers, volumes, and networks. For example, when the developer executes Docker build, the daemon builds the image. When the developer executes Docker run, the daemon creates and starts the container. When the developer executes Docker pull, the daemon downloads the requested image from a registry. The Docker client and Docker daemon may run on the same computer. They can also run on different machines and communicate over a network. Now let us move to the Docker host. The Docker host is the machine where the Docker daemon manages Docker resources and where containers run. It can be a developer's laptop, a physical server, a virtual machine, or a cloud server. The Docker host contains four important types of Docker objects: images, containers, volumes, and networks. Let us start with Docker images. A Docker image is a read-only template used to create containers. It contains the application, runtime, libraries, dependencies, and configuration required to start the application. For example, an image for a Spring Boot application may contain a Java runtime and the application jar file. An image is not a running application. It is the packaged blueprint from which Docker creates containers. Next, we have containers. A container is a running instance of an image. When the Docker daemon runs an image, Docker creates a container and starts the application inside it. One image can be used to create multiple containers. For example, we can use one Spring Boot image to start 3 separate containers. Each container runs as an isolated process, but containers share the operating system kernel of the Docker host. This makes containers lightweight and fast to start. Next, we have Docker volumes. Containers are designed to be replaceable. If important data exists only inside a container's writable layer, that data may be lost when the container is removed. A Docker volume stores data separately from the container's lifecycle. This allows the data to remain available even if the container is stopped, removed, or recreated. Volumes are commonly used for database files, uploaded content, and other persistent application data. Next, we have Docker networks. Docker networks allow containers to communicate with one another. For example, a Spring Boot container can communicate with a MySQL container through a Docker network. Containers can use container or service names to find each other when they are connected to the same user-defined network. Networks can also help isolate communication between different groups of containers. The next major component is the Docker registry. A Docker registry stores and distributes Docker images. Docker Hub is a popular public registry. Companies can also use private registries to store their application images securely. The Docker host communicates with the registry using pull and push operations. Docker pull downloads an image from the registry to the Docker host. Docker push uploads a tagged local image from the Docker host to the registry. This makes it possible to build an image on one machine, store it in a registry, and run the same image on another machine. Now let us understand the complete build flow. The process normally begins with a Docker file. A Docker file is a text file containing instructions for building a Docker image. It may specify a base image, copy application files, install dependencies, expose a port, and define the command used to start the application. The developer executes the Docker build command. The Docker client sends the build request to the Docker daemon. The daemon processes the Docker file and the provided build context to create a Docker image. Docker stores the completed image on the Docker host. The image is a built and versioned application package. Next, the developer executes the Docker run command using that image. The Docker daemon creates a container from the image and starts the application inside it. If the requested image is not available locally, Docker normally attempts to pull it from the configured registry first. Let us summarize the complete architecture. The developer enters Docker commands. The Docker client sends those commands to the Docker daemon through the Docker API. The Docker daemon performs the requested operations. The Docker host stores images and runs containers. Volumes preserve important data. Networks enable container communication. The Docker registry stores and distributes images. Finally, remember this simple flow. A Docker file provides the instructions. Docker build creates an image. Docker run creates and starts a container from that image. A registry stores and shares images, volumes preserve data, and networks connect containers. That is how the main components of Docker architecture work together